Let's see. Okay, so we're going to try and see if we can straighten out 8.5 problem 3. One is this is the question I'm supposed to be discussing, yes?
Yes, that's correct.
Okay, cool. All right, so first things first. Oh, first things first, I need to go get my Laplace transform sheet. How do I know? Ooh, zeroth thing, zeroth. Um, I think I need to rewrite this right-hand side because currently it's piecewise. I would like to rewrite that into some variety of hues, right?
Okay,
So,
see, this is what I did not do. Um, can I check to see if my solution method is valid or if it's complete bullshit?
yeah, hang on one second. I'm gonna.
Yeah, we can see one note.
Okay. All right, Ethan. What was your plan here?
So earlier in the chapter, there's a solution method they bring up, and it worked for the first problem, but it doesn't work for the rest of them, which leads me to believe that it isn't actually viable. But I went ahead and tried it, and it doesn't seem to work. So what they did is they basically decomposed the piecewise function
Mm-hmm.
into two standard functions. So if you call that whole piecewise function f,
Okay.
then they decomposed it into f naught and f1. So f0 and f1. And with f0 being the top one and f0 being, or sorry, f0 being the top function, so f0 equals 4 and f1 equals 6.
Okay.
And then what they did is they basically substituted f0 in place of f. So they got the differential equation y double prime minus 2y prime equals 4.
Okay.
And then they solved that via Laplace transform.
Okay. Cool.
Then they did the same thing for the other one.
So y double prime minus 2y prime equals 6.
Yep. And then they solved that one via Laplace transform. But the only difference is that since it's an IVP,
Mm-hmm.
right, they, used the initial values in solving the left one,
Yep.
but then they also evaluated the left one at the discontinuity point. So at
Mm-hmm.
1, once they got a solution. So they evaluated the derivative of the final solution for the left one and the final solution for the left one at 1,
Yep.
and then used those as the IVP parameters for the right-hand side equation when solving it instead of the original parameters.
Yep.
And then they substituted both of those back into a piecewise function at the end, both of the solutions, and that's the solution. And then if you convert that into the form involving the Laplace unit step function,
Mm-hmm.
theoretically it should match the result from solving the whole thing via Laplace transform of the piecewise in terms of the unit step.
Yes.
But when I did that, the answer is either slightly different in a way that I can't figure out if it's just a different form of the correct answer or if it's actually wrong, or I get to a certain point in the solution process where I have to take the Laplace transform of like a 10-term polynomial fraction and it stalls there. And I can't tell if I'm doing something wrong algebraically or if this is just an invalid solution method.
This solution method should be equivalent to the other one. I'm not sure where we would get a large term Laplace, but maybe let's go see. Um,
You wouldn't mind,
so
yeah. I'm sure I just made a mistake somewhere. I was kind of on a caffeine high yesterday, so I may
okay,
have.
so would you? Which way shall we approach? Do you want to approach in the split way, or do you want to approach as rewriting f in terms of unit steps?
Well, I actually, my brain works a lot better with the split method for some reason, mostly because I understand how to do Laplace transforms of polynomial functions really well at this
Okay.
point. So, and obviously I do know how to use the unit step function, but I find it way easier to avoid it in this case.
Okay. Yeah, let's try it. So, in this case, we are going to start with this one, and then this one we have some like these are going to be at 1, and I'm just flat not sure for these right now. So
Yeah.
I'm going to set this part aside. I'm going to turn this green, and then we can just set it aside for a little bit.
Oh, are you kidding me? I think I know why I got it wrong.
What?
So the problem that you have is y double prime minus 2y prime,
Mm-hmm.
right? I wrote down y double prime minus 2y.
Yep, that'll get you each and every time.
Yeah, I think that might be it. Are you kidding me? All right, well, let's go through it anyway,
Yeah.
just to see if I understand the process correctly.
Okay. Yeah. So transcription errors I find are the most the one of the more common and also the hardest to spot. If you walk in the math lab or come ask me a question, the very first thing I'm going to do is I'm going to go to the book and check that you wrote down the problem right. It does. It doesn't sort out every issue, but it does sort out a number of them, and it sorts them out really fast. All right. So first things first, I need to Laplace transform both sides of this thing. The right-hand side is particularly easy in that I get 4 over s. The left-hand side means that I need to go find the Laplace transforms of a derivative somewhere.
It should be noted that I don't know if this is allowed, but I used the Laplace transform shortcut equation for second order differential equations with a polynomial right side function.
And that would be what?
Laplace of the solution is f plus a times the quantity y naught prime plus y naught, etc.
Feel free. I just don't like memorizing formulas.
Okay, I just found that one to be really convenient.
Yeah, it is. That's a good point. I already have this, so I'm doing this.
Cool.
All right, so I have got my Laplace transform of y double prime. I need to be subtracting twice, and I need the Laplace transform of y prime here. So we're just going to drop that in. Oops. Okay. All right, so we've dropped some stuff in. Now we need to drop in some initial conditions. And so our initial conditions are that y of 0 is negative 6. So that's going to be negative 6 there. That's going to be negative 6 there. Y prime at 0 is 1. And so all told here, I'm going to end up with s squared y minus 2sy. And then let's see, I got a plus 6s and a minus 1 minus 12. So I think I got minus 13 is 4 over s. This is the point where I need an arithmetic double check from you guys. Let's see. So that should have been plus 6 times minus 2 and then minus 1. I think I'm good. Objection?
That looks correct.
Okay. All right. So then we need to move this stuff to the other side. So I've got s squared minus 2s is going to be 4 over s minus 6s plus 13. Oops, that was all times y. So then y is 4 over s times s squared minus 2s minus 6s plus 13 over s squared minus 2s. Now comes the part where I need to partial fraction decompose. So I'm going to go somewhere and find a chrome tab. I really wish we could not do that. All right. Let's see. I need Symbolab. Okay, let's get a format here. Y, no, go back. Thank you. Okay, so on top I have 4 minus 6s squared minus 13s. I just jammed all this stuff together. And then on the bottom, I have an s and a s squared minus 2s. Oops, that's all going in the exponent. That's not what I wanted at all. Okay, objections to that. 4, 6s squared minus 13s all over. I think I'm good. Okay, so in the end, I got, oops, where are we? Right there. Ooh, 23 halves. What an excellent number. This is gonna be the best.
Hey, Joe.
Yes.
Weren't the signs of 6s and 13 supposed to be opposite in the fractional decomposition? You have minus 6s plus 13.
Oh, they were. Good. See, I told you that was going to be a problem. Yep, absolutely. So, partial fractions is jacked because I can't do arithmetic. Good call, Ethan. That should be a... So it should have been... Isn't that what I had? No.
No, you had minus. Yeah, that looks correct.
Perfect. All right, different messy coefficients. Okay. Perfect. Thank you, thank you. Okay, so I got y is this stuff. All right, now I need to be inverse Laplacing. Yes? Maybe?
Yeah.
Okay. So ultimately, out of this, we are going to end up with lol y is minus 15 halves. And then, I don't know the Laplace transform of s squared off the top of my head.
I believe...
I know you know it off the top of your head. You be quiet.
Okay.
I'm really just making a point that I haven't looked this one up. To my knowledge, I haven't looked this one up yet in here. So here's me looking this one up. Let's see. I'm supposed to be finding the inverse Laplace of 1 over s squared. So I'm thinking here 1 over s squared. I think that means n is 1. Does that check out?
Yep.
Okay, so that is the Laplace transform of t. So I got minus 2t. And then I got here a 3 halves, and that is an e to the
2t, I believe.
And don't feel bad if you haven't memorized these yet. If you have to go look them up, it's no big deal. Okay, so that is my y of t. Now, the problem is that that's only valid, right? So really the kind of heart of this issue is that this thing is valid when my right-hand side is 4, which means that this thing is only valid between 0 and 1. Now I need to know what happens when the right-hand side becomes 6, which means that I need to restart this problem in green. Jordan, you're looking at me skeptically. Maybe you're just looking like you have to sneeze. Okay. Perfect. All right. So in order for me to start the other problem, right? So in order for me to go back up to the top here, I need to know what y of 1 is, because that's the initial conditions for this 6. You guys see that? Okay, so in order for me to know that, then I have to say, all right, so y at 1 is minus 15 halves minus 2 plus 3 halves e squared. And I also need y prime at 1. And y prime at 1 is going to be, well, I need to take the derivative of this crap. So y prime at something is going to be minus 2 plus 3e to the 2t. And so y prime at 1 is going to be minus 2 plus 3e squared. Okay, now what?
Do it all again for the second.
I don't know. I need to go back up to the top, right?
Yeah.
So these guys, horrible
Really
as they
quickly,
are,
is the reason why you chose y evaluated at 1, is that because 6 starts at the value t greater or equal to 1?
Yep. Yeah, that's exactly what's going on there. That's when my green function kicks in, right? Like it's blue until times t equals 1, and then it kicks to green. And now the problem that I'm going to have is that green's about the initial conditions for green are at 1. In the Laplace transform, the initial conditions need to be at 0. So I'm left with this kind of like, oh shit. I'm going to have to figure out how to shift this thing around a little bit. Does that kind of thought process make sense? Ethan, can you guess why I prefer the U's now? Cool. Ethan dipped out on me, or okay, good. Oh, sorry. People watching a video won't be able to see. I got a chat message that said yep. Okay, this was at 1, which is maybe not, that symbol's not totally obvious here. Okay, so this is my initial condition now for green. And my differential equation looks like this. Now, I would be in a real world of hurt here. Was I planning on Laplace transforming this to solve it? You guys see why? So if I was planning on Laplace transforming to solve this, I would need to know about y at 0. And so I need to adjust this thing a little bit. That's going to be a giant pain in the ass. I'm going to just flat avoid it right now because I see that I can solve that thing using an easier technique. What's the easier technique to solve this thing? Is there anything inherently Laplacian about this problem right now? Not really. What is it? Well, it's oops. It's a second order linear constant coefficient non-homogeneous ODE. And I know how to solve those. Right? Solve the homogeneous thing and then use variation of parameters or method of undetermined coefficients. Easy peasy. Plug in your initial conditions to solve for your C's. That's about what I'm going to do with this, to be honest. Let me solve this problem the other way. Or at least give a flavor as to how to start it the other way. So if you were going to start this the other way, which I think is the right way, the right thing to do is to take this right-hand side that f of t we were talking about before, and just write it as unit step functions. So initially, this thing is 4, right? Starts at 4. So I'm going to say it's 4. Then what happens at time t equals 1? Well, something happens at time t equals 1. So I'm going to have a plus a u of t minus 1 and a minus u of t minus 1. Okay, so what does the function turn into at time 1? Turns into 6, right? So what we're going to do at time 1 is we're going to turn 6 on. Now, this is a little bit like going in and out of rooms with a parent who's super concerned about electricity use. So if you go into the 6 room, before you go into the 6 room, you have to turn off the lights in the 4 room. So this is me turning off the lights. Right, so I'm going to turn 6 on and I'm going to turn 4 off. Now, I didn't actually have to do that. I'm sure you guys recognize that really the net here, these two collapse together into +2. That makes sense, right? The difference between 4 and 6 is 2. At time t equals 1, I turn that extra 2 on and bam, there we go. Everybody good with this? Okay, so now we can Laplace transform. We already have a lot of the Laplace transform stuff written down. So I'm going to go snag some stuff. So the left-hand side was this stuff. Same procedure, right? Laplace transform, drop your statements about derivatives in here. Now the right-hand side is the thing that changes. So we're going to have on the right-hand side, I'm going to have the Laplace of 4. That's going to be 4 over s. And then here I need, and I'm going to be really kind of explicit here, I need 2 times the Laplace transform of u of t minus 1. Okay. So I'm going to look at my table. I'm going to go find u of t minus tau in my table. I get that the Laplace transform of u of t minus tau is e to the minus tau s over s. So I'm going to get a 4 over s plus 2e to the minus s over s. And then on the other side, I've got s squared minus 2s times my capital Y plus 6s minus 13. And then we're going to see a lot of the same stuff here, right? You guys see that? So after I subtract my 6s and my 13 to the other side, I'm going to have s squared minus 2s times my capital Y is going to equal 4 over s minus 6s plus 13 plus 2e to the minus s over s, and then we're going to divide a little bit. So we're going to get y is, and then this thing here, that's all going to end up being the exact same thing it was before, right? So I'm going to get a 4 minus 6s squared plus 13s all over s times s squared minus 2s. The thing that's really going to be different here is that I'm going to have this 2e to the minus s over s times s squared minus 2s. You guys all on board with this? Good? Bad? Otherwise? Okay. All right. So now I'm going to have my partial fractions kick back in the exact same way they did before. So this one I'm going to go cram into a tool. I'm going to get this. And then this other guy, and this is the thing that's going to let me deal with the rest of this problem, right? So far, I've got basically just the blue thing all over again, right? Like this part here is the blue part. It's just happening again. This thing here is going to be the green bit, right? So I need to get out my partial fractions calculator, and I need to calculate the partial fraction for the top this time is just 2. Okay, so we got some pieces here. Okay, so here is the green thing. What have I lost? I always lose this.
E.
Good. I lost my e to the minus 2s here. So this whole thing, each of these guys, or sorry, e to the minus s. So each of these guys has an e to the minus s on top. Okay. All right, so my next task is going to be to inverse Laplace transform this stuff. I already did that when I solved the blue one, so I'm just going to go grab that. Okay, so I got the blue pieces, and now I just need to inverse Laplace transform this thing. Well, these are a little weird, but they're not particularly crazy. So here's the line I'm looking at. So this is my plan, right? This is the line I'm looking at. And I'm thinking to myself, all right, whoa, okay. So each of these pieces I'm going to split up just a little bit before I do any inverse Laplacing. I'm just going to scoot this down. So the right-hand side is what I need to see, right? So I need to see e to the minus something times the Laplace transform of a function I know. So what I'm going to do is I'm going to just split this thing up, pulling the constants out and getting those e's out. So I'm just rewriting this, and it's only so I don't screw this up, because I personally have a real tendency to screw this part right here up. Like this is in my opinion, the hardest part of differential equations is just getting these inverse Laplace transforms right. So I have a minus 1/2 e to the minus s times 1 over s. And I'm thinking 1 over s is the Laplace transform of, the Laplace transform of 1. Then I have a minus e to the minus s times a 1 over s squared. And I just did this one earlier. I'm pretty sure that's the Laplace transform of t. Then I have a plus 1/2 e to the minus s, and then I have a 1 over s minus 2. And that is the Laplace transform of e to the 2t. Are you good with these? Okay. So now the way these work is these guys here, these functions are little f of t, little f of t, and little f of t. So let's see. I just need this part. Oops. You guys see something I screwed up here? I made a notational boo-boo and you guys just let me do it.
There's no inverse Laplace notation.
Sorry, I didn't
There's
hear you.
Laplace notation anywhere. That's one.
Yeah, I didn't explicitly say that I was inverse Laplacing, but I should have been right here. Right, the step from here to here was inverse Laplace transform.
And now you've got Laplace terms with non-Laplace terms.
Yeah, except I inverse Laplace transform the blue parts, right? But not the black or the green. Ugh, come on, Joe. That's bad. Don't do that. You guys with me on this? So this blue part really should. I was kind of moving along here, and I was inverse Laplacing certain terms and not others. That's like you go through an antiderivative, right? And you like anti-differentiate a couple of things, but not the others. Well, come on, dude. Need some notation. So let me fix my notation. This was little y now, because I inverse Laplace transformed it. This stuff is all inverse Laplace transformed. And then the thing I'm working on is I'm working on inverse Laplace transforming all that stuff. So down here, I'm going to have a little y. And now we're going to fix our green problem, right? So we're going to have minus 1/2. Okay, what's tau for all of these? In all of these things, what's tau?
1.
Yeah, tau's 1 in all of these. How do I know? Well, I'm looking for this e to the minus tau s part, and I'm just matching. Up here I have e to the minus s's. That means you're looking at tau as 1. So that means that on this left-hand side, right, the side I'm going to, I'm going to have u of t minus 1s times f of t minus 1s. So here, I'm going to have a u of t minus 1. That's from the e to the minus s part. Then here I'm going to have something weird. I'm going to have 1 evaluated at t minus 1. What's 1 evaluated at t equals t minus 1?
1.
Yeah, that's just 1. You guys with me on that? Then my next bit here, I'm going to have a minus. This e to the minus s is going to kick a u of t minus 1. And then here I'm going to have t is my f of t. So I'm thinking f of t equals t, but I need to evaluate f of t equals t at t minus 1. So that's going to give me a t minus 1. And this is one of our limitations of algebraic notation, is here we have u at t minus 1 times just t minus 1. You good on that one? Hey, Bridget.
Hi, how are you?
Good.
It's got my real name this time. Cool.
All right. Everybody good at that? That's a weird step. Okay. Our next step is we're going to have a plus 1/2. And now I need a u of t minus 1 again. That's from the e to the minus s, right? And then here I should have scooted all this crap over. Oops, except that one. Okay, so right here, I need, well, right here, I need e to the 2t, but evaluated at t minus 1. So I need to put in t minus 1 into the t. Is that making sense? Okay. All right. Then what? There are so many steps. I'm so lost. What am I doing next? What was I supposed to do to begin with? I was supposed to solve this differential equation to begin with.
I think you're done, aren't you?
You could combine terms.
Yeah, we could combine some terms, but frankly, I'm kind of done. Let's just like logic check our plan here. So back at the beginning here, I had some kind of springy thing, right? It starts with an external force of something, and then that external force changes at time 1, right? So I've got spring gizmo going on, and then at time 1, there's some shift. But it's a shift from a constant to a different constant, right? You guys all see that? Okay, so if I go down here and look at what I ended up with, I ended up with this kind of, why is this blue thing, right? And all the rest of this green stuff is 0 until we get to time 1, right? Because all of that stuff has these u's that don't kick on until time 1. So it's this blue thing initially. That's the same blue thing I got from just solving it set equal to 4 earlier. Right? So that's just kind of how my spring works initially. And then at time 1, when this flip is, or when this switch is flipped, when this flip is switched, when the switch is flipped, the green stuff comes on. Well, remember, we were just switching from a constant to a constant, and so my expectation is that the blue stuff will probably just change by some amount, right? So if I look at the green, notice that for each term, there's kind of a corresponding term. So like, there's a constant. That's just going to adjust the constant. There's a linear term. There's an adjustment to the linear term. There's a e to the 2t. There's an adjustment to the e to the 2t. Okay, cool. That makes sense. This feels like it's probably right. And in the other approach, I would have had to do all this re-indexing. That re-indexing is all of this right here. Right? I'd just be re-indexing by t equals t minus 1 in order to do this. I'd get this same stuff. That's where this evaluating at t minus 1 stuff comes from. Because the time 0 for this e to the 2t is a different time 0 than it is for this one. Does that thought process kind of make sense? Does that square out the difference between the two approaches, Ethan?
Yeah, no, it makes a lot of sense.
I'm going to tend to use the. In fact, I'm going to consider going back and editing the other one out of the book because this is the approach you want. The other one is doable, but it creates that nasty re-indexing that you have to do. And as I have proven multiple times, re-indexing is hard. I tend to get it wrong, and so does everybody else, because it's hard. And that's okay. Okay. Cool. Circle this. I have so many colors going on. Let's just give that a big fat circle. Move on with day. Boom.
Cool. I'm gonna have to dip out, but thanks, Joe. I appreciate it.
Yeah, no problem.
Bye.